Referring to this diagram, this figure, basically we can see something about this, that we can say that lambda naught, if I say, let's say KCl minus lambda naught NaCl, that is at infinite dilute solution, I am talking about KCl and NaCl, has been found to be equal to lambda naught KNO3 minus lambda naught NaNO3. This was the wonderful observation by Cold-Russ. And then he certainly said that how it is possible. Just look at over here. If I say lambda naught K plus lambda naught Cl minus, that is at infinite dilute solution, cations and anions are free to move. Resistance is very, very less. Conductance is maximum. Over here, lambda naught Na plus minus lambda naught Cl minus. If I see in the left hand side LHS, we get this. So that means cancels out. You get basically lambda naught K plus minus lambda naught Na plus. If you talk about right hand side RHS, also you get same lambda naught K plus lambda naught NO3 minus lambda naught Na plus minus lambda naught NO3 minus. Quite naturally this cancels out to get lambda naught K plus minus lambda naught Na plus. It means that left hand side equal right hand side. So therefore these values are coming to be equal, and Cold-Russ said that yes, let's say for lanthanum chloride LaCl3, which gives you La plus 3Cl minus, so you write lambda m naught of LaCl3 is equal to lambda naught La plus 3 into lambda naught Cl minus. So this is what this situation is. That means how many cations, how many anions, 1 mole cation, 3 mole anion, summation of this two will give you the lambda m naught of LaCl3. With the help of this, he basically found out how to find out lambda m naught of acetic acid. He said that lambda naught acetic acid, now it is very easy to find out lambda naught acetic acid. How? If you take lambda naught CH3COO plus if you take lambda naught HCl, and if you minus lambda naught NaCl, just you'd see over here you are left with basically lambda naught acetate and lambda naught H plus, because you know these common parts will be cancelled out, so therefore we will get this, and this is a molar conductance at infinite dilute solution. Molar conductance at infinite dilute solution, of weak electrolyte acid is acetic acid, which was impossible to find out from the diagram, as we have found that this is like this. So therefore it should meet at infinity. No, now we will put over here somewhere over like this, and this is the lambda m naught acetic acid. And that is the beauty of Cold-Russ's law of independent migration of ions, and of course the concept of Debye-Huckel-Onsager equation. What I said is equal to lambda naught minus b root c. Already I said this is basically Debye-Huckel-Onsager equation. Debye-Huckel-Onsager equation. This is quite complicated equation, all statistics involved, but at our level we are not going to go into the depth of this, how the derivation has come out, but thing is that this is very important at the 11th and 12th level. So therefore now in using Cold-Russ's law, now what could not be explained with the help of the Debye-Huckel-Onsager equation, which is basically applicable for the strong electrolytes, not for weak electrolytes. Now Cold-Russ's law of independent migration of ions tells us that what is the molar conductance of the weak electrolyte like acetic acid. So that is the beauty of this acid. So these kinds of things come in your exam curriculum and subject curriculum. So you should be aware of the fact that anytime strong electrolytes can be decomposed, you can take the components of the cations and anions. For example, few more examples. If I say, let's say, what is lambda naught molar NaCl, I can write in aqueous solution with lambda naught Na plus lambda naught Cl minus. It is all molar. I'm talking about is all molar especially. Now talk about lambda naught equivalent. Lambda naught equivalent will be equal to lambda m naught divided by n factor. So it's very, very important, lambda naught equivalent n factor. So for example, let's say I'm talking about, let's say AlCl3. If I take lambda lambda naught AlCl3, lambda naught molar AlCl3 is equal to lambda naught molar Al plus 3 into lambda naught molar Cl minus. But if I say lambda naught equivalent AlCl3, that is 1 3 lambda naught Al plus 3 plus lambda naught Cl minus. So that means what you can see that matching this two, you can get 3 into this will be equal to lambda naught molar. That means we can say 3 into lambda naught equivalent of AlCl3 is equal to lambda naught. It is 3 lambda naught equivalent AlCl3, lambda naught molar AlCl3. So this is very, very important that lambda naught equivalent is into n factor is equal to lambda m naught. That is, molar conductance of infinite dilute solution will be equal to n factor into equivalent conductance of infinite dilute solution for a strong electrolyte. Now I will talk about the application of conductance. Application of conductance measurement. Application of conductance measurement. Very, very important measurement. Applications of conductance measurement. Number 1, finding out the acid dissociation constant or base dissociation constant for weak acids or weak bases For example, I am taking, let's say, in this container we are taking acetic acid having 2 electrodes like this. Of course I will be measuring with AC current because there shouldn't be any this thing, the electrolysis of this. So if I talk about acetic acid, let's say CH2COOH, that is CH2COO minus plus H plus. So obviously if we say C moles, initially T equal to 0, C molar, so T equal to T, it is basically C into 1 minus alpha, it is C alpha molar. So now we know the undissociated acid cannot carry electricity. Electricity can be carried out, can be flown. Electricity can move through the solution by the ions, and of course if the ions are more in numbers, obviously conductance increases with increased dilution. So quite naturally, but here just look at over here, let's say I am taking the velocity of the cation is U plus under unit potential gradient. Velocity of cation under unit potential gradient. Why we are talking about unit potential gradient? This is all physics. Potential gradient, let's say it is U plus and of anion U minus respectively. Why I am saying so? For example, physics, V equal to I into R. So if I write V by R, we can write V, let's say V by R is equal to what? I, and so obviously if V is equal to 1, then 1 by R equal to I, so that means conductance equal to I. For molar conductance I'm talking about. So therefore, now what is I calculation from this? I at concentration C, we can say C molar, we can say I equal to current carried by the cation towards the electrode, plus and minus. So let's say it is negative, it is a positive, so it will go towards this, So quite naturally, I equal to I plus I minus. That is current carried towards the cathode, and current carried towards anode is the cathode, and it is anode. We are talking about it is anode, positive plate. When it is positive, then it is anode. When it is negative, then it is cathode. So current carried by the positive charges to the cathode plus current carried by the negative charges towards the anode. Sum of this is I. So what is I plus? We can write that. Let's see, I am talking about N plus and N minus are the cations and anions per unit cc. So therefore we can write, if I say if the velocity is U plus, just look at over here, if the negative plate like this up to this, whatever the anions are there, whatever the positive charge, there is cations are there, those will be basically depositing on this electrode. So what is this length? It is basically U plus. So that means we can write N plus is the total number of cations per unit cc into U plus into area, for example A, and let's say Z plus into E. Just look at over here, number of cations per unit cc. Over here I am talking N plus. That means what? It can be C alpha is the molarity. So C alpha by, if I say V liter, so it is a C alpha into V is basically number of moles of cations into Avogadro number is the total number of C alpha is the molarity. So C alpha by V, that is V liter, in V liter C alpha, so 1 liter C alpha moles. So C alpha by V into Na is the total number of cations into U plus into area into Z plus into E. If I say area is 1 square centimeter, that also we can make, plus we can say for the anionic part is I minus is N minus into U minus into A, area of observation. We can say this initial area we can make 1 square centimeter. Let's say A equal to 1 square centimeter when taking about. So it is over 1 over here. Over here it is 1 square centimeter. Then N plus U, N minus U minus into, we can say Z minus into E. And what is N minus? We have to substitute N minus by basically C alpha moles of acetate divided by V into Avogadro number multiplied by U minus as velocity and unit potential gradient into 1 into Z minus into electronic charge Z. Electronic charge Z is the charge of electron. And here Z plus and Z minus are the charge of cations and anions. Charge of cation and anion. So this is what the concept is, and V is the volume of the solution in liter. V is the solution in liter. So quite natural, this is what the lambda molar is at this concentration. But if I talk about whole at infinite dilute solution, then the whole acetic acid has decomposed, they are dissociated into cations and anions, then we can write lambda m naught, that is equal to C alpha. Instead of C alpha, I'll write C by V into Na, because we know that all acetic acid has dissociated into cations and anions. So at infinite dilute solution, C acetic acid will give you C molar cation, C molar anion. So therefore you can write into U plus into 1 square centimeter into Z plus into E plus C by V into Na multiplied by, we can say U minus into 1 into Z minus into E. So therefore let's say this is equation 1. Let's say it is equation 1, it is equation 2. With the help of that, you will be saying that lambda m by lambda m naught. What is that? That is basically, if you see, whole the terms gets cancels out, all cancels out. So all cancels out. So you left with alpha. That is degree of dissociation. Degree of dissociation. If it is so, degree of dissociation, quite naturally, as we know, this is the equation C1 is a Ka acid constant. So what is K by equilibrium concept? K equal to alpha C into alpha C divided by C into 1 minus alpha, giving rise to alpha square C by 1 minus alpha, giving rise to lambda by lambda naught square C divided by 1 minus lambda molar by lambda molar naught is basically this. So for the corresponding weak acid, same thing applies with weak bases. So it is very, very important to us to how degree of dissociation being calculated. It is all electrochemistry, helps us basically to find out the Ka, Kb. Even we'll see KSP in the next slide. We'll find KSP, and I will show you the how KSP is also the solubility product of sparingly soluble salt is found out.